Section 8.7 is Taylor and Maclaurin series. It's our last series section for this course, and it's our most versatile tool for power series, and it's essentially everything we're going to do with it in this course. Now note that these things are useful later on in differential equations and all kinds of applications where you might want to estimate functions which are a bit more complicated than ones you could easily take derivatives and integrals of. So the first thing we should see is that the coefficients for function f, its coefficients in a power series, these are the c sub n's here. If it has a power series of this form, then its coefficients should satisfy the formula given here. In other words, we can find its coefficients via this, or if we have a power series, it should be the case that this is true. Okay, that each coefficient is equal to that. Now, let's confirm that that's the case in the previous example. What's really useful about this is we see that if f is a differentiable function, then we can take, well, if it's n times differentiable, then we can find up to its nth coefficient. If it has infinitely many derivatives, then we could take infinitely many of these coefficients to form, infinitely many of these derivatives to form each of these coefficients c sub n. It's a really powerful tool because now we can build power series for any differentiable function f or any infinitely differentiable function f. So let's expand that power series just a moment and have a look at the details of this. F of x is now written in this form, right? The nth derivative of f evaluated at a. Notice that a is the center of this expansion, the center of this power series. So we're evaluating the nth derivative of f at a for the nth term and dividing by n factorial. When we do that, when n equals 0, we've got just f of a. This is to the 0 power, so it's 1. 0 factorial is 1. This is the 0th derivative of f at a, which is just f of a. Next up, n equals 1, we get f prime of a for the first derivative. Then we have 1 factorial in the denominator. We have x minus a to the first power. So, and we continue to do this. That's a first order term. And in fact, if we cut it off right here and just looked at this section, this should be recognizable. We can drop the 1 factorial. It's just equal to 1, so we can throw that away. But f of a plus f prime of a times x minus a, that is exactly the linear approximation of f of x at a. And what we recall from Calc 1 is that f of x, so for some value of x, we can plug it into the function f. It's approximately equal to the value at f of a plus the derivative of f at a times x minus a. In other words, remember that this on the right-hand side is a line. We called it L of x. It's the linear approximation of f at a. And it does a reasonable job of approximating f near a. So the function f near the value a. The further we get away from the value a, if this x value is further and further away from this value of a, well, then the less accurate this approximation is. Okay, but we can fix that by adding more terms. If we add more higher order terms, these are called the second derivative of f, then the third derivative of f, and so on, then we can make this approximation even more accurate. As soon as we add this term, note that we have x minus a squared. And that's no longer a line. Altogether, if we just had these three terms, we'd have a parabola. X minus a squared is introducing a quadratic term. We're going to have an x squared in there with a coefficient. If we did all the work to factor this all together, we could write down what this parabola is and graph it. And we could see that it will closely approximate, if our function f looks like this, then it would closely approximate, f near some value a. And it would do a better job than, say a line would do, the tangent line. Okay, so that's the idea as we build these polynomial or these infinitely long polynomials that as they run out to infinity in terms, they're exactly equal to this function, but we won't always need that. We'll just run it out as far as we need, cut that term, the remaining terms off, and we'll have an accurate enough approximation. So that's one of the main uses of Taylor and Maclaurin series. Now, what are Taylor and Maclaurin series? Well, they're power series. It's just with coefficients given as this. So this is a Taylor series expansion of f around a. So in other words, it's this arbitrarily long approximation of f. It's the extension of the linear approximation. Now, when the center A is 0, we have a special case, and that's the Maclaurin series. So the Maclaurin series is when the center is 0, which just slightly simplifies our expressions. We don't have x minus a's in here anymore. We just have x to some powers. So Maclaurin series are a little bit easier to deal with. But of course, you want to be able to move the center wherever you like, because you might need to just approximate a function near a certain value. And if it's nowhere near 0, then you're going to need a lot of terms in your Maclaurin series in order to get a close approximation or an accurate approximation. So let's verify that these coefficients are actually true. Is this actually how this should be? So we're going to sketch a derivation of this formula. In other words, that C sub n should be equal to the nth derivative of f evaluated at a. And we're in fact going to do that for the more general Taylor series rather than the Maclaurin series. So we assume that f of x is equal to this power series. Okay, for some radius around a. It could be only at a, or, I guess it does. We are given that the radius of convergence is greater than 0, so it has some non-zero length interval around a for which it converges. Now, if we write out a few terms, we'll notice the following. We have C naught plus C1 times x minus a, and so on to higher order terms out to the nth term here and beyond that. And think about if we have f evaluated at a, f of a is equal to, we plug in x equals a. The only term that survives x equals a in this expression is C naught. Everything else is zeroed out when we plug in x equals a. So f of a is C naught. Okay, so C naught, these Cn, these coefficients are unknown. We're proving that these coefficients are actually the nth derivative of f evaluated at a over n factorial. Okay, so we see immediately, though, that f of a is C naught. So we've got that. Now, f prime of a, what happens here? If we take the derivative of f with respect to x, C naught's a constant, so it becomes 0. There's no factor of x next to it. This leaves us with C1 times 1. The derivative of x minus a is just 1. This is 2 times C2 x minus a. Everything else has an x minus a in it after that first derivative. So when we do f prime of a, all the x minus a terms will cancel to 0 from that derivative. C naught already went to 0 because we took the derivative of f and it was a constant. The only term that survives is C1 times 1. And well, so it's just C1. So f prime of a is 1 times C1, or just C1. Similarly, take the second derivative of f. Now C naught goes. C1 is just C1 times 1. Take another derivative, and that becomes 0. Now 2 derivatives have happened here. We're down to just an x minus a times 2 times 1 times C2. And that's exactly what we have here. Everything else evaluates to 0 when we plug in a to the second derivative. And we do that up to the nth term and realize that by the time we get there, it would have been multiplied by all of its exponents here, counting down n and then times n minus 1, just as we saw 2 times 1. For f, the third derivative of f, we'd have 3 times 2 times 1. So we're seeing that's 3 factorial there. This one was 2 factorial. In general, it's n factorial times c sub n. So this last expression that we get as our general term, we solve for c sub n to see that c sub n is in fact the nth derivative of f evaluated at a divided by n factorial. And that matches this exactly. So not all the language is there for a formal proof, and we could have probably demonstrated some of this a little bit better, but I think it's pretty clear. Maybe if you write out f triple prime and the fourth derivative of f and so on, you can convince yourself that this is actually in fact the case, and it leads us to this conclusion. So now we know for certain that this, if a function f has a Taylor series, then c sub n is definitely given by this formula. So let's use it now that we're convinced that it's the case. They ask us to find the Maclaurin series for the function f of x equals e to the x. Now, I might have hinted at this one in the past, but we're actually going to do this directly. They also ask us to find the radius of convergence for it. So we know that c sub n is generally given by the nth derivative of f evaluated at 0 over n factorial. Now, sometimes there's a nice pattern here. Most of these problems will have a nice pattern, so it's worth writing down the first four coefficients, or developing the first four coefficients. In order to get there, we need to take the 0th derivative of f, which is just f of x, and that's, well, f of x is e to the x, so we write that down. Then the first derivative, f prime is e to the x, f double prime is e to the x, same thing for f triple prime. Now, the next step, we need to evaluate each of these derivatives of f at 0. In other words, we plug in 0 everywhere there's an x for each of these. We have that f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. And, well, the nth derivative of f is always e to the x, so evaluating at 0 is always going to be 1. So this is a really simple coefficient. C sub n is just 1 for all n. And we see that, I'm sorry, it's the nth derivative of f evaluated at 0 is 1 for all n. But remember, there's one more part of this formula we haven't taken care of yet. And all we have to do for that is write n factorial in. So c sub n is f's nth derivative evaluated at 0 over n factorial. All of these are 1, so we have 1 over n factorial. And that's our coefficient for all of our e to the x power series terms. So we write that in as follows. E to the x then is equal to its coefficient times x to the n. Now, this is a center of 0. It's technically x minus 0 to the n because they asked for the Maclaurin series. So the center is 0. That's also why we evaluated at 0 here. So this is x minus 0 to the n, or just x to the n. Now we write what c sub n is, and that's an easy formula we were able to get over here. So it becomes series as n equals 0 to infinity of x to the n over n factorial. Okay, we've actually done this before. We checked the radius of convergence for this exact power series back in 8.5, I believe, and we found that this thing had a radius of convergence which was equal to infinity, which means its interval of convergence is all real numbers. So you could confirm that again for practice, or just find the notes where we did that previously. Remember, it's the ratio test and setting the conditions of convergence for the ratio test and determining which x values satisfy those conditions. And you'll find that it's all real numbers. So validating Taylor series, this is not something I'm going to spend much time on, but it is nonetheless an interesting result. The book spends a little bit more time in the examples, in the exposition for this section to show how this is done. I won't spend too much time working the example, but I will say that we know that a function is equal to its Taylor series. And we call this the nth degree Taylor polynomial, T sub n. We'll see this in a few places. We'll be asked to come up with the 10th degree Taylor polynomial. In other words, find T10 or take it out to an x to the 10th expression. Okay, R sub n of x is that remainder of the series, and that's just starting after the 10th term and working out towards infinity. Now, what we've seen with these series problems in the past, or these series representations, or any of these power series we've dealt with, or numerical series, is that oftentimes these tails tend to get smaller and smaller. Remember that the denominator of each of our terms in one of these series is n factorial. So as n goes to infinity, n factorial gets exceptionally large. So that's how we're able to throw away these infinitely many terms in the tails and still get accurate approximations. So anyway, if we split f of x up as its nth approximation plus the remainder, which makes up the entire series altogether when we add them, then and we have that the limit as this remainder goes to 0, which is something we'd have to prove on a case-by-case basis, for x minus a within its radius of convergence, which is capital R here, not to be confused with the remainder R sub n of the series. then f is equal to the sum of its Taylor series within its interval of convergence, which is written here. Okay, so a useful way to show that this thing is equal to 0, this limit goes to 0, is to recognize that there's a bound here on r sub n of x that we can use. Now this is where m is the bound on the n plus 1 derivative, the n plus first derivative, which is interesting to note. That's the term after our last term in t sub n. That's good to know. But if we can bound the n plus first derivative of f by some value m, then what follows below will be very useful. And again, this is for some x values within a distance d of a. So in other words, within some interval of convergence for our power series. But this is a bound on this remainder. N will be fixed because it's bounding the n plus first derivative, or it might be a function of n, quite possibly, over n plus 1 factorial, and then times x minus a to the n plus 1. And this is for, again, x values that are centered around a, but within a distance d of a. So what will typically happen when these things work is we'll just see that this n plus 1 factorial will overpower all the other functions of n that are involved here. So, but to see that, you'd have to do it explicitly. I believe the book has at least one nice example of that. I don't assign many problems with that, so we don't need to dwell on it too long. But there is a means of validating that these Taylor series are in fact equal to their functions on their intervals of convergence. Okay, so let's do some more work finding these series. Maclaurin series, they ask us to prove that it represents cosine of x for all x. I think that what I'll do is save this for our live meeting this week, and I'll cover that there. Again, it doesn't come up in any of the exercises, I don't believe, certainly not on the worksheet, and most likely not on a test. So maybe other than getting through a few problems in WebAssign, we don't really need to prove that these series represent their functions. So what I'll do here is just find the Maclaurin series for cosine of x and call it partially done. So remember that the Mclaren series is the nth derivative of f at 0 divided by n factorial for our nth term, nth coefficient. Now f is a little bit more, it's got more richness to it than e to the x does in terms of its derivatives. It's cosine of x. So we start taking derivatives. F prime is negative sine x, then f double prime is negative cosine x, then f triple prime is sine of x. The fourth derivative of f is positive cosine of x when we step down from sine of x, and we're at cosine of x, and then we repeat. So we do at least have this cyclic behavior. And we'll evaluate all of these derivatives of f at 0. Notice I went out to a fifth derivative this time instead of just the fourth derivative, or maybe even just the third derivative like before, because I wanted to sort of convince myself that there's a pattern here. And we see that, yeah, when we evaluate at 0, it's there. If we weren't sure, we could add a sixth line or a seventh line and really try to show ourselves or convince ourselves that a pattern does exist. We don't have to prove it, we just have to find it and use it. So f of 0 is cosine of 0. Cosine of 0 is 1. F prime of 0 is negative sine of 0. Sine of 0 is 0. And we just move on down the line. Negative cosine of 0 is negative 1. 0, 1, 0, working down from these trig functions. So we see that we're alternating between ones, negative ones, and zeros. And well, when we go to write this down, we'll say, okay, cosine of x then is equal to its coefficients, which we are kind of getting the hang of at least. We know the top part. We might have an idea of the top part of these coefficients, given as nth derivative of f at 0 over n factorial. And the center is 0, so it's x minus 0 to the n. So we just have x to the n here. So we write each of these down. This is 1 is our first coefficient times x to the 0 is 1. So we just have a 1 down here. And then we've got 0 is our second term in our series, because our second coefficient, C2, is 0, because f prime of 0 is 0. what we've seen. And that zeroes everything out for that term. F double prime is -1 over n is 2 for this term, so over 2 factorial. So we have a negative, and then it's over 2 factorial. N is 2, we have x squared. So that's that term. Now the term after that for the third derivative, which is our fourth term, or n equals 3 term, our f triple prime of 0 is 0. So the numerator here is 0 again, so we just have a 0 for that term. Okay, so our coefficients are going to zero out all of our odd terms. So we don't have any odd terms in this, so we won't see any odd powers of x or odd factorials. Our fourth term, x to the fourth, this is when n is equal to 4, has a positive 1, so over 4 factorial. We have x to the fourth over 4 factorial then. There's x to the fourth times 1 over 4 factorial. So what will happen is we'll alternate plus or minus signs, and we'll only have even terms. So the next term after x to the fourth over 4 factorial is negative x to the sixth over 6 factorial, and so on to x to the eighth, alternating signs, and we have only even powers of x over even factorials. Well, the exponents match the factorial, so it's a nice, easy rule to write down. Cosine is a somewhat similar Maclaurin series, and we'll see that in just a second. So sometimes getting from here down to here can be a little tricky, but oftentimes we could see the pattern. And what I encourage students to do is, don't just look at a blank page here. Write down a rule that you think makes sense, and then write out a few terms that that rule or that recipe would generate, and see whether or not you're getting the series that you had. If not, make adjustments. That's a nice guess and check way to get there. You're not really guessing. You're guessing this general rule, but it's just helping you work out what those details are. So let's see another one. So find the Mclaren series for sine of x and state with justification its interval of convergence. Okay, so see that momentarily. Sine of x. So we had from our previous example that cosine of x has a power series, or a Mclaren series, given as -1 to the n times x to the 2n over 2n factorial. Now what we could do, we could ignore that result and say, well, I'll come over here and I'll do my usual Maclaurin series work. I'll have f of x as sine x, then I take f prime of x as cosine x, and f double prime, f triple prime, f the fourth derivative of f, so on until I feel like I've got enough terms to establish a pattern, and I can do all the work I might need to there. Or we can use what we learned in 8.6 and say, well, sine of x and cosine of x are related. And they're related by the fact that if we integrate cosine of x, we'll have sine of x plus a constant. So maybe we just let that constant be 0 in this case, just to simplify things. Now let's see. Sine of x then is equal to the integral of cosine of x. So that's the integral of this power series. And luckily in the last section, we saw how to integrate power series. So we know that we can exchange that integral sign with the summation. So this new series that we should get is the summation of anything that doesn't have to do with x can move out of the integral. So in other words, this integral sign has moved from here to here, but then -1 to the n and 2n factorial aren't functions of x, so they can move all the way out to here, and we're just taking the integral of this function of x to the 2n. It's a pretty easy integral to take. You add 1 to the power of this expression here, so we have 2n plus 1 in the exponent. You divide by that new value, 2n plus 1. So we have x to the 2n plus 1 over 2n plus 1. These two terms have been consolidated as one fraction here. And when we look at this, we have 2n factorial times 2n plus 1. Well, we're stepping up one value above 2n, multiplying it by 2n factorial. That's just 2n plus 1 factorial. The reader can check that by writing out the first few terms of 2n plus 1 factorial. Now, that's sine of x. That was sort of easily done, easily handled. We didn't add the constant. We'll just let that thing be 0. Let's have a quick look at what these terms look like. And by letting that constant be equal to 0, by the way, we get the conventional, the standard power series representation of sine of x centered, this is Maclaurin series, so it's centered at 0. And it's exactly what you would get if you did things the long way off to the side here. The long way is also good practice, so I certainly encourage that. But we don't always have to do the long way for these problems. Now, the first few terms of this, when n is 0, this is positive 1, this is x to the first power. So there is no constant here for this function over 1 factorial. So our first term is an x. And then the next one should be negative, and you'll find that the next term is actually x cubed over 3 factorial. When n equals 1, 2n plus 1 is 3. So we have a 3 here and here. So the first two terms are x minus x cubed over 3 factorial. And sine does something very similar to cosine. It alternates plus and minus signs, and it only includes odd terms, whereas cosine only included even terms. So if you remember from trigonometry, sine of x was an odd function, and it only has odd polynomial terms, so it's an odd polynomial, it's an odd power series, which is consistent with the fact that it's an odd function. Cosine was an even function. It only has even powers of x, so it's only an even power series, if I might make up a term for a second. Even power series, meaning that it only has non-zero coefficients for the powers of x that are even. Anyway, we have one more task left to do for this problem, and that's to determine its interval of convergence and justify it. Well, in order to do so, we just go right back to our old power series radius and interval of convergence work, and we take the ratio test of our power series, and we find the x values that satisfy the limit of this ratio being less than 1. So I've written it all in one big step here. We've got some practice with this by now, so we know what we're doing. Here's our n plus 1 term. Here's our n term for sine of x. That's coming right out of this recipe. I've ignored the negative 1 to the n terms because we have absolute value bars, and those will have no effect whatsoever on this overall expression thanks to the absolute value bars. So group the factorials together, group the powers of x together. That's what we have below. So we have this expression, these powers of x as a ratio, and these factorials as a ratio. Well, note that 2n plus 3 is a factorial that is 2 steps above 2n plus 1. Otherwise, it contains 2n plus 1 factorial. So what we have in the denominator is 2n plus 3 times 2n plus 2, because the next step down is 2n plus 1 factorial, and that canceled with the 1 up here, with the 2n plus 1 factorial here. So that's why we're left with just 2 terms in the denominator as functions of n. Now x is just x squared from simplifying this. X has nothing to do with this limit. N runs off to infinity. This term is driven to 0. This is strictly less than 1. We see all this summarized here. So as soon as we get that this overall limit here is 0, doesn't even have x in the expression, well, then we know that it doesn't matter what x is. This is always true. Right? Our limit is the left-hand side is always less than 1. It's true for all x values. So we know that the radius of convergence is infinity. The interval of convergence is negative infinity to infinity. So maybe we did it opposite. We justified our answer and stated it in the end. That's just the usual workflow for finding the radius and interval of convergence for a power series. It's nothing new, nothing different from what we did back in section 8.5. So let's find the Mclaren series for a slightly more complicated function, x squared times the sine of x. So it's still a Maclaurin series, so we're still dealing with centers at 0. What we could do is we could start out just the long way. F of x is x squared sine of x. F prime of x is this product rule. But note that this could get really tedious. The second derivative, then we've got to do a product rule here and a product rule here, and we're going to keep propagating more and more terms. In fact, it looks like we're probably going to have 2 to the n terms for the nth level. That's just a guess, but something like that is most likely true because these x squareds never go away. So it's just going to grow and get larger and larger, and that's not going to be any fun. So let's be a little bit more clever about this. Let's remember that sine of x already has a Maclaurin series that we know, or a power series centered around 0. So if we already know a function's power series, Taylor or Maclaurin or whatever it is, if we're looking for one with the same center, in this case the center is 0 all around, so yeah, we're just fine. Then all we have to do is see if we can manipulate the given power series to come up with the new one. So x squared sine of x is x squared times this power series. That's exactly what we have here. Well, n equals 0 to infinity, that has nothing to do with x, so we can multiply x squared by the series term, because after all, it's going to multiply by all of them anyway. And what does that do? Well, it matches up with this base, x and x, and we add 2 to 2n plus 1, and we get 2n plus 3. So our power series has just barely changed. None of the stuff involving n changed, which makes sense. This is just x squared. But we were able to just rewrite this whole thing as a power series by saying, okay, everything is up by 2 powers in x. And this would be exactly the power series for this function. You don't always get such a short, quick, and easy trick, but you should always keep an eye out for it, because this would be a nightmare. So again, just to make a comment, x squared sine of x, this is not an easy function to integrate if we were to consider that. Remember, much of Calc 2 is about integration. That's much of our purpose. So since this wouldn't be an easy thing to integrate, what we could do is say, well, let's take the integral of its power series. Power series are very easy to integrate. The only thing involving x in here is this highlighted bit right here, x to the 2n plus 3. So the integral of this power series is just the antiderivative of x to the 2n plus 3. So it adds one thing. We have to divide by its new power, right? We add 1 to this and get 2n plus 4. And then we divide by that new power, which is 2n plus 4. So that has to show up in the denominator. But otherwise, we've got exactly an indefinite integral for this function. We were able to handle that indefinite integral and write it down as a power series. Then we've added our constant c, just to be more general about this. We're not actually looking to get to anything, so we'll leave that unchosen, right? We'll leave it arbitrary. So it's not a closed form of this function, so it has some drawbacks. We couldn't write this down simply in finitely many terms. It has infinitely many terms. However, it's a good representation to have for this function, for this function's antiderivative, because if we needed to approximate it somewhere, well, and we were close to 0, since this is the Maclaurin series for this function, we're close to 0, we need to approximate the definite integral. Say we're going from maybe -1/2 to +1/2. This might be ideal to use. So we could do that by evaluating this function at +1/2 minus the evaluation of this at -1/2. It's the second time I've hinted at something like this. We'll actually do this in detail by the end of this section. So one more before we get to that approximation business. Let's work with a Taylor series just to see how this goes. Find the Taylor series of f of x equals natural log of x around the center a equals 3, or around a equals 3. So c sub n is the nth derivative of f evaluated at 3. So the key thing here is we don't have the nth derivative of f evaluated at 0. It's evaluated at 3. That's the new center. That's the thing students forget to do sometimes. Change that center to match what it should be. This makes this problem a little bit more complicated to deal with. Anyway, first things first, just write down f of x, f prime of x, and so on until you think you've got enough terms to sort of pick out a pattern. Well, f of x is natural log of x, then f prime of x is x to the -1. The derivative of this is -x to the -2. The next derivative starts to get a little more interesting. -2 times -1 here is 2 times 1, x to the -3. The next derivative is going to be a -3 that comes down times these terms. So we have -3 times 2 times 1, x to the -4. So we see that there's a factorial thing that's happening, factorial pattern, thanks to these powers of x that keep stepping down. as we take derivatives. So we'll keep track of that. Now, we still need to know what the nth derivative of f is, though. So we'll handle that factorial in just a moment. And altogether, let's see what happens with this 3, though. F of 3 is the natural log of 3. There's not much we can do about that, so we'll just write it down as is. Now we have f prime of 3. This is 3 to the negative 1 times 0 factorial. I've added 0 factorial because 0 factorial is 1. Technically, that thing is times 1. Next up, we've got 1 factorial in front of this, and there's a negative sign as well. This is 3 to the negative 2. So keep writing that. Now we've got 3 to the negative 3 times 2 factorial. So we see that we're getting alternating plus or minus signs. If we start at this term and work our way down, we'll alternate plus, minus, and we're just growing our factorial terms. And we see that we're also growing the exponent of 3. It's 3 to the negative 1 to the negative 2 to the negative 3 to the negative 4. That's pretty easy to see the pattern for. Each of those matches what derivative we're at, the nth derivative. So we will stick with that. Now, one thing we have to be careful about is the fact that this is only true when n is greater than or equal to 1. Right? Also note the factorial situation. First derivative, 0 factorial. Second derivative, first factorial. Third derivative, 2 factorial. So the factorials are down 1 from the derivatives. So when we talk about the nth derivative, we should have n minus 1 factorial, as we've written here. Now we also know that when n equals 1, we're here, this is positive, so this is negative 1 to the n plus 1. And that's going to make it positive for all our odd terms. And notice that our odd terms are the positive ones here. And lastly, the easy one to spot was that 3 to the negative 1 matches the number of derivatives we're on. F double prime is 3 to the negative 2. So this is just to the negative n. So this is a bit of a tangled mismatch of terms, but if we write down enough of these lines, and we are careful about pulling things apart and recognizing how these numbers relate to the derivatives, then we'll get a nice general term for f sub n at 3. This is exactly what we have right here. Now, this is only true for n greater than or equal to 1 because this is a bit of an oddball term. It's not going to ruin our day. We're just going to add it to the power series, and we're going to start this thing at n greater than or equal to 1. So let's get there momentarily. So if this is our nth derivative of f at 3 with a general formula here, then our coefficient c sub n is this thing divided by n factorial. So now we've got, here's our f sub n at 3, and then divided by n factorial is underneath n minus 1 factorial. So we can simplify n minus 1 factorial over n factorial, and that cancels to just an n in the denominator. In fact, n factorial is n times n minus 1 factorial. So we're left with just a nice clean n. We still have our alternating negative 1 to the n plus 1 term, and 3 to the negative n is just, well, we can put 3 to the n in the denominator, and that's just the same. This is only true for n greater than or equal to 1 because, of course, we can't capture with this pattern this natural log of 3. So natural log of 3 will just really be our constant that we add to this power series. So natural log of x is n equals 0 to infinity, c sub n of x minus 3 to the n. Okay, so we're ready. This is our Taylor series expression right here. We have our coefficient. We only know it for n greater than or equal to 1, or we can only write it for that. So we'll put our extra term on the outside, and we'll start not at n equals 0, but at n equals 1. We write down our c sub n as is. We've got it right here. And then we have x minus 3 to the n, and that's exactly what we write right here. And to take care of our 0th term, we just add natural log of 3 outside of this power series. So this is the Taylor series of the natural log of x centered at 3. So there's quite a bit more to go. This is a great start. We've done several Mclaren series examples so far. This is a Taylor series example. From here, we'll finish up with some more Taylor series. We'll do some of those approximation techniques. We'll even see building new series from old within this Taylor and Maclaurin context. So that'll be in the second video or the next video for 8.7.